Hello, everyone. Good evening to all of you. Today, I'm very happy to present a new work on geometry group theory, and we will discuss some of the basic ideas surrounding that work, and then I will also tell you what is new in this particular paper. This has been sponsored by Cheenta, this particular research. So, thanks to Cheenta for that. And it's also part of the geometric group theory research group at Cheenta. If you are interested to know more about it, you can go and visit cheenta.com. This particular paper, as you can see, the title is Connectedness of Bowditch Boundary of Dehn Fillings. It is an extension of the work of Groves and Manning, Daniel Groves and Jason Manning. I will share the links of their papers in the description as well. And it also uses some results from a previous paper of myself with Christopher Ruska. And it also uses some tools related to JSJ decompositions by Girdle and Levitt. I'll talk a little bit about it, but first I want to give you a sort of an overview of what this is about. Basically, when you talk about relatively hyperbolic groups, you have to first understand what we are talking about, because this is a very special class of groups. It's a large class of groups. Actually, it's a group pair. What we do is we look at a group G. In this case, we are only looking at finitely generated groups G. And in those groups, let's call it capital G, the finitely generated group, let's call it capital G. And then we specify a certain set of collection of subgroups of G. Let's for the moment assume that all of them are finitely generated. Then this group G and the collection of subgroups, the group G and the collection of subgroups, they're together called a group pair. Now, in certain situations, this group pair can have some nice properties. Now, of course, I don't have time to describe those nice properties today, but they have certain geometric properties that allows us to study them, study their group theoretic properties using more of a geometric approach toward them. So in those scenarios, that group pair is known as a relatively hyperbolic group pair, a relatively hyperbolic group pair. Now, one technique to study such relatively hyperbolic group pairs is to understand a certain type of topological space on which these groups are acting. If you are familiar with group actions, you know that, well, groups can be regarded as topological as actions on certain kind of spaces. Sometimes they can be regarded like that, and it's often useful to study that particular space. It often useful to study that particular space and the action to understand the group theoretic properties, the algebraic properties of the group. Okay, so that's exactly what we do. We start with a relatively hyperbolic group pair, and then we specify a topological space. In this case, we specify a topological space called the Bowditch boundary, on which the group has a very nice action. A very nice action that tells us more about what the group theoretic properties of the group is. Okay, so now that this is set up, let's talk about the other important tool that we will be using in this particular talk, called the Dehn fillings. The Dehn fillings. Okay, so Dehn fillings, if you are not familiar with the name of Dehn, you can definitely Google it or try to find it online. It's a very very interesting story about there are geometric Dehn fillings. You can look into the work of Thurston, for example, and there are group theoretic Dehn fillings, which has been studied by people like Groves, Manning, and Osen. I will just put the paper's link in the description so that you can look into the material, the associated literature. So what they essentially do is that they quotient out these peripheral subgroups. Remember, we started with a group pair where G was a group, and then we specified some of the subgroups of the particular group G. Those subgroups, the ones we specified, those subgroups are called peripheral subgroups. Now, what we do is in Dehn fillings, in group theoretic Dehn fillings, what we do is we quotient out those peripheral subgroups by certain normal subgroups of those peripheral subgroups. In a way that shrinks the entire complexity of the group. May not actually happen. Sometimes it could get more complex. In fact, in certain situations, the boundary of the Dehn fillings can be more complex than the boundary of the original group. But let's not go into the more complex part. In principle, what happens is you quotient out some of those peripheral subgroups and you reduce the complexity. That's what happens. Okay, so what you do is you then study the boundary of the Dehn fillings. So you had the boundary of the original group pair G and a collection of subgroups of G, P1, P2, P3, let's call them the peripheral subgroups. And then what you do is you quotient out the peripheral subgroups, and you get in something called a filled in group. It's called those that particular quotient map is sometimes called the group theoretic Dehn filling or the map of Dehn filling, but it essentially reduces the complexity. Okay, so now let me talk a little bit about the work that has been done. Okay, so in their paper in 2009, which was published in 2018, Groves and Manning show that there are a couple of things that we extend actually in this particular paper. So I'll talk about both of them. The first one is the theorem 1.6 in the Groves Manning paper. Again, I'll tell you an overview. What is the big picture story of their work so that you understand. What they essentially said is that under certain conditions, the Dehn fillings cannot be factorized if the original group cannot be factorized. Remember, I talked about splittings some times ago in another seminar here. If you were there in that particular seminar, that's great. If you were not there, let me quickly say a couple of lines about it. Just like numbers can be factorized, for example, 30 can be factorized into 5, into 2, into 3. Similarly, groups can also be sort of factorized. Sort of factorized. So, what do I mean by that? So, if you are in college or university, you have heard about graph of groups decomposition. The essential idea is same, that if you have a large group, and it's hard to study that group, why don't you break it down into smaller pieces? This is called a splitting of a group. Just like a number can be splitted into product of two or three numbers or more numbers, similarly a group can be also splitted. Now what Groves and Manning shows is that if you have relatively hyperbolic group pair, and if that cannot be splitted, if the original group pair cannot be splitted, there is a certain kind of splitting that they are talking about. It's called elementary splitting. So they assume that suppose there is no elementary splitting, of the original group pair, there is no elementary splitting. So if you don't know what is an elementary splitting, don't worry. for the moment, just think about it as a kind of factorization of the group. Okay, so it says that if the original group does not admit an elementary splitting, then if you fill in that group, that is quotient out the peripheral subgroups, remember that's the meaning of filling. If you fill in that group, then the filled in group also will not admit any elementary splitting. So in a way, if the original group cannot be factorized, then the filled in group also cannot be factorized in a certain way. Okay, that was the theorem that was there in the paper of Groves and Manning 2018 paper, but they had a certain condition. The condition was this, that these groups, the peripheral subgroups, uh, well, the actual condition was like this. Sorry, the condition of the peripheral subgroups was in theorem next one. In this one, the condition was on all small subgroups. So there are certain subgroups of a group called small subgroups, and they assumed that all the small subgroups are finitely generated. All the small subgroups are finitely generated. This is a type of restriction on the hypothesis. So under this restriction, that all small subgroups are finitely generated, Groves and Manning could show that if the original group did not have a factorization, the filled-in subgroups will filled-in group also will not have a factorization. So notice this particular line that is given in this particular theorem. Suppose that all small subgroups of G are finitely generated. That is part of the hypothesis. That is, G, the original group, G must satisfy this condition for their theorem to work. For the theorem of Groves and Manning to work, you need all the subgroups of G to be finitely generated. Again, the original, the big picture idea is absolutely simple. You start with a group pair, that is a group and a collection of subgroups. Then what you do is you do a Dehn filling, that is you quotient out the collection of subgroups by certain normal subgroups of those subgroups. So you get a quotient group of the original group, and you want to know if the original group cannot be factorized, is it true that the filled in group also cannot be factorized? So Groves and Manning said, yes, that is true, provided this additional hypothesis that the group G has this condition that all small subgroups of G are finitely generated. All small subgroups of G are finitely generated. So this was the condition. So one of the work in this particular paper is that we removed this restriction from theorem 1.1. So instead but then we had to actually change the hypothesis a little bit more. We were looking into a little bit different type of splitting actually, but under certain different assumptions. If you are familiar with these kind of stuff, then of course this different assumption is that we assume that the splitting is relative to the peripherals. So in a way, we assume that the peripheral subgroups are not doing anything very interesting in a way. Okay, so the splitting is relative to the peripherals. If we assume that, then that extra condition on small subgroups in is not necessary anymore. That's number one. That's the first upgrade or a different variation of theorem 1.2. A more interesting, I would say, work is theorem 1.4, which is an upgrade of theorem 1.9 of Groves and Manning. Remember, I talked about the boundary. So it is natural to ask that if the original boundary is connected, is the filled in boundary also connected? If the original boundary of the group pair is connected, is the filled in boundary also connected? That is a natural question to ask, and Groves and Manning actually responds to that question. They say yes, that is true, provided again there is a restriction on the peripheral subgroups. They say that okay, Yes, the filled in boundary will also be connected. Filled in boundary will also be connected, but but you have to assume that the peripheral subgroups are all virtually polycyclic. So that's a special type of subgroups that they are restricting the peripheral subgroups to. So we change that particular theorem. We actually uh, remove that particular restriction, and we show that no matter what, if the original boundary is connected, then the filled in boundary will also be connected. There are that's the that I would say that this is the more important theorem in a sense. Okay, in a more important removal of restriction. Now, to prove this theorem 1.4, the basic structure was this, that we show that under certain condition. So first of all, I use the other theorem that we proved in a previous paper with Christopher Ruska. It's a joint paper with Christopher Ruska, that the Bowditch boundary, if it is connected, then it is locally connected. Okay, so that's a major tool in this particular theorem 1.4. The other factor, that the other tool that we use, is a major structure theorem related to art trees. It's a very fascinating part of mathematics, the art trees. If you are interested in that, you can also check out the work of Bestvina. There is an expository article by Bestvina on art trees and group theory and so on. So uh, we show that we use a tool, that is a structure theorem for art trees. This tool was created by is due to Gödel and Levitt. It's called a relative version of a Rips machine. Now, Rips machines have been very useful in mathematics, for in group theory and topology and so on, for the last 20-30 years. The relative version of Rips machine will be particularly useful in this particular problem. So I will put a preprint of it in our website and all. You can check it out if you are interested in the actual application. So that's how we prove theorem 1.4. This as of today, this is 18th September. I think on 20th September the preprint is supposed to appear in archive. If you are interested, you can check that out. And if you are interested in stuff like uh, group theory in topology and geometry group theory and so on, you can definitely talk to Cheenta, or people in Cheenta will be very happy to talk about it. There are several research groups which are working on different parts of mathematics in Cheenta, apart from doing Olympiad mathematics and stuff like that. As I say, my entrance problem solving and so on. It's a fascinating world. If you are interested to talk more, we will be very happy to do that. Thank you for joining in today. Some of you were school students, and some of you are college students. If the words seem a little bit difficult to you, let me tell you this: it's actually not that difficult. Once you get hold of the vocabulary, you will probably be finding it much easier than you think it is. It is actually, it's just the vocabulary can be a little bit troublesome at times, but once you understand what the words mean, trust me, these are not at all that hard. It's very fun to think about these things, so I encourage you to do that. And hopefully I'll see you in the next one. Okay, all right, thank you guys. Thank you for joining in today. It was lovely to see so many of you joining in. Bye. And I will respond to the questions in the comments which are not related to this paper. In later, you can ask, if you are an internal student of Cheenta, you can ask it in the personalized WhatsApp groups and so on. Okay, bye.